Hello everyone. This is your course instructor Monisha Rajkech, Assistant Professor, Department of ECE, Sai Vidya, Institute of Technology. In this lecture video, we'll be starting with Module 3 of Information Theory and Coding, that is Information Channels. Before going into the actual contents of or in depth of this module, we'll first see what are the contents in this module. So it goes as follows. It consists of three parts. So first part contains communication channels, discrete communication channels, channel matrix, joint probability matrix, binary symmetric channels, as well as system entropies. The second part of this module consists of mutual information, channel capacity of binary symmetric channels. And the last part consists of binary erasure channel and Muraga's theorem. This is the contents of module 3. Next, we'll go in depth about each of the topics. The first topic is channel communication. A practical communication system is divided into a transmitter, physical channel or transmission medium, and a receiver. The transmitter consists of an encoder and a modulator, while the receiver consists of a demodulator and decoder. A channel can be defined as a medium through which the coded signals generated by an information source are transmitted. The block diagram that you see in the slide shows the characterization of a binary communication channel. That is, a point between C and G that you see in the slide is a discrete channel, often referred to as coding channel, that accepts a sequence of symbols at its input and produces a sequence of symbols at its output. The communication channel between points D and F in the system provides the electrical connection between the transmitter and the receiver. The input and output are analog electrical waveforms. This portion of the channel is often called as continuous or modulation channel. An example for this channel is high frequency radio system. The points between B and H, we have binary data being presented at the input and binary data back at the output. And hence, the channel is called as data communication channel and it is discrete in nature. After knowing about the characterization of the binary communication channel, that is about the data communication channel, coding channel, and modulation channel, next we'll be seeing about disturbances in the channel. In channel, there are various kinds of disturbances. These disturbances may be due to amplitude and frequency response variations of the channel, and also due to non-linearities in the channel. All these disturbances introduce errors in the data transmission and limit the maximum rate at which data can be transferred over the channel. An important characteristic of a data communication system is the channel capacity, which represents the maximum rate at which data is transferred across the channel with a small probability of error. This is about communication channels. Next, we'll be studying about discrete communication channel. The communication channel, what we have seen in the previous slide, the point between C and G is discrete in nature. In general case, the input to the channel is a symbol belonging to an alphabet of M symbols. The output of the channel is a symbol belonging to the same alphabet of M input symbols. Due to the errors in the channel, the output symbol may be different from the input symbol during some symbol intervals. Errors are mainly due to the noise in the analog portion of the communication channel. The discrete channel is completely modeled by a set of probabilities, that is PIT, where I varies from 1 to M, and PIJ, where I and J varies from 1 to M. PIT is the probability that the input to the channel is the ith symbol of the alphabet, and Pij is the probability that the ith symbol is received as the jth symbol of the alphabet at the output of the channel. This is a brief idea about discrete communication channel. Next is, in the binary case, we have statistically modeled the digital channel, that is as shown in the figure or as shown in the slide. So, this figure is the model of a discrete channel. Errors occur in random fashion, and the occurrence of errors can be statistically modeled by assigning probabilities to the paths, which is shown in the figure, where P00 plus P01. What do you mean by that? P00 means the input, what you send, that is the zero input sent will be received as zero itself at the output. P01 in the sense, the zero input sent at the transmitter will be received as 1 in the receiver. That is the errored bit. So combination of these two equal to 1. And here we are representing transmitted bit as T and received bit as R. So this is about discrete communication channel. Next, a memoryless channel. If the occurrence of an error during a bit interval does not affect the behavior of the system during other bit intervals, then the probability of an error can be evaluated as P error equal to PE equal to P of X not equal to Y. This can also be written as P of X equal to 0, Y equal to 1 plus P of X equal to 1, Y equal to 0. The probability of error can also be written as P of X equal to 0 into P of Y equal to 1 by X equal to 0 plus P of X equal to 1 into P of Y equal to 0 by X equal to 1. We can further simplify this and can also write it as PE equal to the transmitted bit, that is POT into P01 plus P1T into P10. Next we have one more thing where we can generalize this equation as when a 0 bit is transmitted, what happens, and when 1 bit is transmitted, what happens. So when 0 is transmitted, P0t equal to P0t into P00 plus P1t into P10. But when 1 bit is transmitted, we get it as P0t into P01 plus P1t into P11. This is for a memoryless channel. Next, there is a condition for us to tell that it is a binary symmetric channel. What is the condition? For us to tell it is a binary symmetric channel, the P00 and P11 should be equal to same probability, that is P. Then the channel is said to be binary symmetric channel. So for this binary symmetric channel, we have some parameters that is needed to characterize this binary symmetric channel. For that, we need to consider a model of an M-array discrete memoryless channel. That is as shown in the slide. Previously, we had seen it for just 2 inputs and 2 outputs, but this is for M-array discrete memoryless channel. For this, we'll be defining certain parameters that will characterize the binary symmetric channel. What are those? Before knowing that, we need to generalize an equation for error for M-array discrete memoryless channel. So first we'll see that this M-array channel can be analyzed on the same lines as presented above for the binary, where we had considered only 2 inputs and 2 outputs. So the generalized equation for the received bits is PJR equal to summation I equal to 1 to M PIT into PIJ. This is a generalized equation for the received bits. In the same way, we can write the generalized equation for the probability of error, that is P error, for an M array from the 2-bit or the binary channel what we had seen in previous slides. So it is written as P error equal to P equal to summation I equal to 1 to M PIT into summation J equal to 1 I equal to 1 to M into Pij. This is a generalized equation for P error for an M array channel. Next, we'll see the definitions of different entropies for discrete memoryless channel. The first one is entropy of input x, which is represented as h of x. H of x equal to minus summation I equal to 1 to m pit into log of pit bits per symbols. This is for an input value. We'll see for an output, that is entropy of output y is represented as h of I. H of I equal to minus summation I equal to 1 to m PIR into log of PIR bits per symbol. After knowing the input and the output, we'll know about the conditional entropies. The conditional entropy is represented as h of x by y and is defined as h of x by y equal to minus summation I equal to 1 to m into summation j equal to 1 to m p of x equal to I comma y equal to j into log of p of x equal to I by y equal to j bits per symbol. In the same way, a conditional entropy can also be represented as h of y by x. H of y by x equal to minus summation I equal to 1 to m into summation j equal to 1 to m p of x equal to I comma y equal to j into log of p of y equal to j by x equal to I bits per symbol. After knowing about the conditional entropy, we'll know about the joint entropy, which is represented as h of x comma y and defined as minus summation I equal to 1 to m into summation j equal to 1 to m p of x equal to I comma y equal to j into log of p of x equal to I comma y equal to j bits per symbol. These are the definitions of different entropies for discrete memoryless channel. After knowing this, we'll define or we'll explain what is a conditional entropy. The conditional entropy h of x by y represents how uncertain we are of x. Here we are defining or telling or explaining how h of x by y is represented. So the conditional entropy h of x by y represents how uncertain we are of x on the average when we know the value of y. So we can verify the following relationship between h of x, h of y, h of x by y, h of y by x, and h of x comma y. So the joint probability can also be written as h of x by y plus h of y, or h of y by x plus h of x. That is the combination of conditional probability and input entropy, or the conditional entropy or output entropy. This is about the definitions of different type of entropies. Next topic is rate of information transmission over discrete channel. In the case of an M-array discrete memoryless channel, accepting symbols at the rate of RS symbols per second, the average amount of information per symbol going into the channel is given by the entropy of the input random variable x, and that is given as h of x equal to minus summation I equal to 1 to m pit into log of pit to the base 2. So in this equation 2, we have assumed that the symbols in the sequence at the input to the channel occur in a statistically independent fashion. We have learned what is statistically independent in module 1. So we are telling that we have assumed this equation that the sequence at the input to the channel occur in a statistically independent fashion. Next, the average rate at which the information is going into the channel is given by d in equal to h of x into rs bits per second. So we can say that some information are lost due to errors. Before we attempt to define the amount of information that is lost, let us consider an example. What is that example? Suppose there are two possible symbols 0 and 1 that are transmitted at the rate of 1000 symbols with P0t equal to half and P1t equal to half. The source information rate and D in at the input to the channel are 1000 bits per second. This is an example. So for this, let us assume that the channel is symmetric with the probability of errorless transmission P equal to 0.95. But there arises a question. What is it? What is the rate of transmission of the information? So it is certainly less than 1000 bits per second, since on the average 50 out of every 1000 bits are incorrect. Our first impulse might be to say that the rate is 950 bits per second by subtracting the number of errors from the data rate at the channel input. However, this is not satisfactory since the receiver does not know exactly which bits are in error, even though it knows that on the average 50 out of 1000 bits are incorrect. The inconsistency in defining information transmitted over a channel as the difference between the input data rate and the error rate can be removed by making use of the information lost in the channel due to the errors. To understand this, we have something known as ideal errorless channel. What do you mean by ideal errorless channel? For an ideal errorless channel, we have no uncertainty about the input given. The output and h of x by y is equal to 0. That is, the conditional probability will be equal to 0 and the output will be equal to 0. That is, no information is lost in an ideal errorless channel. So knowing that h of x by y equal to 0 for the ideal case wherein no information is lost, we may attempt to use h of x by y to represent the amount of information lost in the channel. Accordingly, we define the amount of information transmitted over a channel by subtracting the information lost from the amount of information going into the channel. That is, we may define the average rate of information transmitted, dt, as the amount of information transmitted over a channel by subtracting the information lost from the amount of information going into the channel. And it is given by dt equal to h of x minus h of x by y into rs bits per second. This is about rate of information transmission over the discrete communication channel. Thank you.